So this is better. Okay. So like in the last time we studied the Elmore delay, and we said that the basics of the Elmore delay work by if I have a specific path from an input node to an output node, then I really can calculate the effective, RC time constant as from the on-path capacitors and the off-path capacitors. For the on-path capacitor, it is the resistance from the source node to the specific capacitor. And for the off-path capacitor, إذا عندي capacitor مثلا like C4, it is the resistance of the shared path from the input to the output. يعني if this is the path to the off path capacitor، يعني إذا ل C4 في عندي R1 و R3 و R4 to reach it, I'm really not interested in R4. I'm only going to count R1 and R3. So C4 will be multiplied by R1 plus R3 لأن it is the intersection. This is the intersection, okay, between the path between the source and the input output node, and between the source and the off-path capacitor. Okay, so therefore for the on-path capacitors, if this is my path from the source to the output, I really multiply each one, C1 by R1 plus C3 times R1 plus R3 plus Ci times R1 plus R3 plus Ri. And then for the off-path ones, like C4, I only multiplied by R1 plus R3 because I only care for the effect of يعني delay up to this node. I'm not going all the way to C4. So C4 will be multiplied by R1 plus R3, and then C2 in this example will be multiplied by R1. Okay, وقلنا إنه time constant tau هو summation of Ci times the R effective I اللي هن هول quantities for each resistor, and then from this time constant I can find my delays. Okay, then we derived the case of the wire, and we said that for the wire, if I apply the same formula, and the reason I'm repeating this because we're going to add a driver here in a little bit, then really if what's going to happen from the first at node 1, if all of these are equal capacitors, then the time constant tau will be equal to C1 times R1 plus C2 times R1 plus R2 plus Cn times R1 up to Rn. Okay, because this is the path from the input to the output, and every capacitor we will count the resistive path to reach to it on my dedicated input output path. يعني شو هو الريزيستنس اللي يوصلني لعندها على main path is what I count. And from this we derived and we said, well, each one of the Ri هو L over N, and then we said, well, accordingly now I can find this summation, and from finding this summation I will end up with tau being approximately RC over 2. يعني this summation here counts to me as RC over 2, and this is referred to as the distributed wire model compared to the lumped wire model, which is only RC. This is the lumped model is pessimistic. Okay, great. فإذا a line is characterized by little r, which is the ohms per unit length, for example, micrometer, and C is maybe m2 per micrometer, and the big R is really little r times L, and the big C is really little c times L. Okay, and then we said that Elmore delay helps me in many factors, such as if I have devices, path gates, or a wire. And then we said, well, we approximated the delay to be RC over 2, and then we took several examples. Okay, and these examples were related to poly material or related to aluminum wire, and we looked how to calculate from the table the effective capacitance per unit length اللي هي هنحسب الC للفول L من CPP and C fringe. Okay. And then this is multiplied by L multiplied by L بالفرنج حطالينا 2 لأن الفرنجing happens from both sides. And then I find my little c as big C over L. And so we winded up finding that we are approximating little c as CPP plus 2 CF, and it will be in M2 فرد per micrometer. بس طبعا هيدي CPP بقى تنضرب بالwidth للواير لأنه هون ال W كانت equal to 1 in this example. Okay. And then we said, well, CPP I always obtain it from the top line in the poly, and then the second line is the fringing. للألمنيوم 1 نفس الشيء لأنه we're always assuming overfield, aluminium 2 the same, and so on, so forth. Okay. Now I'm being told that I have a circuit that has an effective driver resistance. What do we mean by our driver? We mean that if I have an inverter and I am measuring TP high to low, what I know in the CMOS inverter is for sure that the Rn will be pulling down the capacitor to ground. So my R driver in this example is really Rn of the NMOS transistor. Now here, remember that for us always our problems are like this. I have a resistor that is connected to ground, and then the switch will close and it will start to discharge the capacitor. Here, instead of saying the switch will close, for example, here they're taking the case where the output will go from low to high, and they decided to apply a step input going up. طبعا نحن ما عندنا الانبوت ما عم يتغير على طول عم يوصلني من VDD أو من ground بس the switch is turning on or off, and I have the R driver and then the wire, and they're asking me to find what is the propagation delay for my circuit. So I need to use Elmore delay, and I will use it in a similar fashion as we have done before, and we will find that it is really simple. Okay, so we will find that it is really simple. Let's see what we have here. Okay, so pardon me. Okay, so we had, let me actually clear all of this. It's fine. So we have the circuit. Okay, so we had the circuit. If I want to write now my equations, I am going to represent our driver here, and the distributed model we really have R1, C1, okay, R2, C2, all the way up to Rn, Cn. Okay, and now if I want to find the time constant, all that is going to change is I will have C1 will be multiplied by R1 plus R driver. Okay, so this is R driver here. Okay, and then C2 will be multiplied by what? And this is the input, this is the output here. And so C2 on this path will see the resistance R driver R1 and R2. So it's R1 plus R2 plus R driver. And in a similar fashion, Cn will really see R1 plus R2 plus Rn plus R driver. Okay, فإذا دخلت مع ال R driver into the equation. If I want to rearrange this, I will say that this quantity is really equal to, pardon me, is really equal to, that this quantity is really equal to, let us see, I will take our driver out and I multiply it by some quantity, and this quantity is going to be C1 plus C2 plus Cn. Okay, and then I will have the regular C1 R1 plus C2 into R1 plus R2 This is the regular distributed wire constant that we just derived. طيب. I know that my little c's are, that my ci are the little coefficient c times L over n. So their summation is هيدي البيج N يعني. Their summation, okay, what is their summation؟ شو حيطلع جمع little capacitance؟ big C, right? So this, I will end up here with R driver, okay, times the C of the wire, plus this constant here we already derived it, هيدي CW subscript. This constant we already derived it, it is the R wire times the C wire over 2. Okay, so my new time constant is really R driver times C wire plus R wire times C wire over 2. From here on, I know my tau, I can find all my delays. Okay, anybody has any question? طب great. So لكينا هلا if we come here we will find that the time constant will be R driver plus times C wire plus R wire times C wire over 2, and we know that R wire and C wire are R times L and C times L, so it will be 0.5 times RWCW coefficient L squared. Okay, هلا هاي the delay نحن اتفقنا, we agreed that we're going to say that the delay is going to be 0.69 times tau d times my tau, okay, which in this case will be 0.69 times R driver CW plus 0.69 times RC wire over 2. Okay, يعني delay هو 0.69 time constant, والtime constant happens to be R driver C wire plus R wire times C wire over 2. Okay, where RW هي RW times L, CW هي CW times L. Okay, type great. And then we're going to now look into different considerations, which are when is the wire delay significant, for what length, and when is the, can I ignore it, and stuff like that. Okay, so accordingly, let me just erase this. Okay, so this will be equal therefore to 0.69 times RD times CW plus 0.69 times RW CW over 2. Okay, so the delay introduced by the resistance, by the wire resistance basically, and whole capacitance is affecting the driver, becomes dominant when the time constant due to the wire is appreciable or greater than the time constant that is due to the gate delay driver resistance. Okay, يعني لما term 2 بيصير أكبر من term 1, I can assume that really the wire resistance has some effect. Okay, and now it's just plugging in values and I can really find the relation between the length of the wire, the R driver and the R little wire. يعني هو بهمنا بس هيدا الexpression لأنه the rest of it is really plug in, and I'm going to really replace this as CW times L, and now I can really study the relation between this quantity versus this quantity here and see for what L the wire resistance becomes significant. Okay, so let us take an example. They tell me that for an R driver, and let me just write it explicitly. Pardon me. Okay, so let me okay. Okay, so now I am being given this. Let us see how I can solve for this scenario. So I am being told that I have a R driver is 1 kilo ohm and it's driving a 1 micrometer wide aluminum one wire and L crit is 2.67 centimeters. Okay, and I am trying to really find when the wire resistance significant or not. So let us try to find let us try to find CW and RW. We need to know it, and we also need to know R driver to find those quantities. Okay, for R driver I have 1 kilo ohm. For CW I'm going to have, it is little cw times L, and we said that this is CPP times the width plus 2CF, and we said last time that we need to go back now to the table to see how these quantities matter. So let us check it for aluminium one. The CPP is 30 and the C fringe is 40. So let us populate these quantities here. And so this is equal to 30 times, let us see what the quantities were, 1 micron, okay? This is femtofarad per micrometer squared times 1 micron. So I end up with femtofarad per micrometer plus 2 times 40, which is femtofarad per micrometer. So this is equal really to 30 plus 80, 110 femtofarad per micrometer. This is the little c. Okay, so this is first I am solving here for this little c. So let me remove this. So this is the little c. Okay, and from this little c I can find my big CW, which is the little CW times L. So it will be 110 femtofarad per micrometer times 2.67 centimeter. It is 0.267 meters, so it is 2.67 times 10 to the 5 micrometer. This is the capacitance for my wire. Okay, so let us see how we can now solve for the other quantities. Okay, so let me now, I have solved for the wire, pardon me, I have solved for the wire capacitance. Now next I want to look for the wire resistance. So I need to look for aluminum. I need to look for, aluminum. Okay, we have a table. Either we will give you the resistance for aluminum per unit length, or we will give you a table for the resistance of the aluminum. I think the table we gave it to you in the previous set of slides. So let us say now that I give you that for the aluminum the resistance is, let us assume now that we say that for the aluminum the little Rw, let us say it is 5 ohms or 0.1 ohm per micrometer. Okay, then we will be able to find the R wire. It is equal to 0.1 ohm per micrometer times 2.67 times 10 to the 5, because I need to have Rw is little r times L. Okay, and this way we will end up for it being equal to 2.67 times 10 to the 4 ohms, which is equal to 26.7 kilo ohms. Okay, and then now I have RW, I have R driver, I have CW. I can compare the two quantities and figure out the rest of the information that I need. Okay, type great. So as a rule of thumb, there are different, we need to relate when do I consider the wire delay and when not to consider it. I need to relate the L in terms of the delay of the gate and the 0.69 but times little RC. هيدي rule of thumb. You don't have to worry about it. Let us always calculate it from the previous quantity that we derived here. Those two quantities that we derived here. Okay. And then there is another rule of thumb is that also if the signal rise time is very slow, then we do not consider too much the RC delay, but if the signal rise time is fast and it is smaller than the RC time constant of the wire, هيدا مثل rule of thumb that the designers take, then I should consider the wire delay. هلا لأنه هي signal rise time كمان it is function of the driver and function of the previous stages, and this tells me really if my wire resistance RC time constant is significant or not. But really what matters is that we are going to say that my delay time constant is 0.69 times R driver times CW plus 0.69 times R wire C wire over 2, and our job really is to weigh in and compare those quantities. That's what we really care for. طيب هلا transmission line effects we are not going to worry about them because they are out of the scope of the course, so I'm going to stop the wire effects here at this slide. Okay, anybody has any questions? طيب okay. Okay, so let me then now jump to the next set of slides where we will, sorry, this is a little bit, where we will look at the inverter delay and then eventually see how to optimize the delay of the inverter chain. So I'm going to take a step forward and then I am going to walk you through the derivation. But like to give you a little motivation as to why we are doing all of these derivations. The idea is that in a big circuit, okay, if I have designed, for example, my ALU, and the ALU is a block that came from another unit or from another circuit, and I have this block which I designed, and I told you that I have designed this block so that it can handle a specific load capacitance which is small, and it will do this function. Okay, and now you're building this, but while you're combining the wire or while you're combining the designs together, you find that you have a very long wire that is going somewhere else in the chip to another module. This very long wire to us, it means a very large capacitive load. Okay, so this means that now all of a sudden I have to interface my ALU with a very large capacitor. I cannot go back and tell the designers fix your ALU and optimize it because this is a module that has to be shared, used everywhere, and it needs to be compact. So facing large wires, what we typically do is we insert buffers, يعني بنساعد الfunction by inserting buffers to be able to drive this large wire. Okay, and we design the buffers that are being, طبعا بدها تكون buffer بدها تكون even number. We design the buffers such that the first buffer interfacing my function has a small cap, and the final, then I size those transistors such that the whole chain of inverters now can handle the large capacitor with minimal delay. يعني أنا my job is to add a buffer made of many inverters such that it can handle the large capacitor with minimal delay. يعني my penalty is the area, without subjecting the previous pre-designed block to the problem of facing the large capacitor. The previous pre-designed block is going to see the small capacitor or the input capacitance of my buffer. Okay, so basically this is the motivation of our work. So we are going to start by looking at the inverter delay reformulated so that it is really dependent on its own capacitance, it is function of its own capacitance and the capacitance of the load or the next stage that it is driving. يعني حنخليه يكون some constant times 1 plus some ratio which represents the ratio of the next size to my size. And based on this, we are going to end up with an optimized formula that can really find this ratio for a given desired input capacitance and final stage wire, the large wire capacitance that I want to handle. Yani the inputs to my problem, which is I want only to be interfaced with some CN, and this is really the wire that I need to handle. We will be able to solve the problem that tells me, well, how many stages I need to insert and what is the sizing or the ratio of these stages. Okay. So that will be our objective. بس okay. Okay, بس bear with me a minute بس 1 minute. Okay, sorry. Okay, so let us now go back to the slides. So now we will go back to the slides and see how we will reach here. هلا the first part of it is good revision for you لأنه it is basic. يعني it will be basic information كأنه review للshort quiz and then we will jump to the formulation. Okay, طيب great. So we will look at delay computation methods. So the methods for computing the delay of the inverter. We said it is the time to go from points 1 to 2. We said that the inverter will have its own self-capacitance, the wire capacitance and the load capacitance. And now we're going to look at two possible methods to calculate the delay of the inverter. The first is the average current method, which you have seen in 311. And the second is using the equivalent resistor from which will stem the rest of the formulation. Okay, so for the average current model, for the inverter driving, we will start from the fact that if I have a resistor that is charging or discharging a capacitor C, or if I have some other device or other driver, okay, since I care to measure the delay on the capacitor, I have since I care to measure the delay on the capacitor, we know that the current of the capacitor is CdV by dt. Then we can say, well, I can find dt of the capacitor as the relation CdV over I, and I can find delta t or the delay of the capacitor if I do the integral of CdV, meaning if I have the integral of CdV over I, right? But what we're going to say is that if we assume that I to be an average current, then this will be equal to C over I average times integral of dV, and this will be equal C delta, and this quantity therefore will be equal to C times, therefore TP will be equal to C times delta V over I average. Okay, فإذا we move from the capacitor equation to derive the delay as the capacitor times delta V, the voltage during which the change on the output voltage or the capacitor voltage during this interval over the average current that was dissipated in this interval. Okay, so let us now see what we are being told here. Okay. So, okay. So, هلا average current method, it says I of t is equal to I average is equal to I of t2 plus I of t1 over 2. Okay, and we approximate the load by a constant capacitor. So if it is some value C, sorry. Okay, let me just make a slide in which I write this. Pardon. 1 second. Because here the equations do not show properly. Okay, and so now the basic idea is that we are going to, okay, so we are going to say that T, or the delay, is equal to C delta V over I average, where I average is equal to I of T1 plus I of T2 over 2. Yani for example, if I have an inverter driving a capacitor, okay, and I know that V out, which is the same as the V capacitor, is going to move from 0 all the way to VDD, okay, or if it is going to move from V init to V final, then I measure the delay. This is time point T1, this is time point T2, okay. At time T1, V out is really equal to V init, and at time T2, V out will be equal to V init plus V final over 2. Okay, so the delta V is really V out of T2 minus V out of T1. And here this delta from here to here, it is this quantity minus this quantity, and the I average is really the I at time point 1 plus the I at time point 2 over 2. So if we take this now to a CMOS inverter, and assuming that we want to approximate the high to low delay of the CMOS inverter using the average current method, okay, then we know that the output, we will assume that the output is going to start in a CMOS inverter at high, which is VDD, and it's going to drop to 0 eventually, okay? So the 2 points that I am interested in are this point T1, okay, and this point here T2, okay, and this point is really the 50% point of the output. Now, if the output is going from high to low, this means that the inverter was subjected to an input pulse that switched high, okay, and this is going to result in the PMOS being off and the NMOS being on, and the NMOS discharging the output so that the output will go high to, okay, so the output will go high to. Under these considerations, we need to define at the 2 time points the current that is flowing in the capacitor. The current that is flowing in the capacitor in absolute value is equal to the current that is really flowing in the NMOS device. Okay, so therefore, okay, if I want to apply KCL, okay, and I want to really look at IC here, okay, this is IC and this is IN, okay, I will have IC plus IN equals to 0, and I will have basically IC equals minus IN, okay, and then if I want to find the delta V, okay, what is the delta V on the V out? It is V at T1 minus V at T2. V at time point 1 is equal to VD, sorry, pardon me, it's V2 minus V1, pardon me. So the delta V is V2 minus VT1. Okay, so this is VDD plus 0 over 2 minus VDD, and this is going to be minus VDD over 2. Now, as you notice here, while we are discharging, the current in the capacitor is negative and the delta is negative, they will cancel each other. So what we can do is really we can calculate the absolute values and use them here on. طيب هلا I need to find IC average. So I need to find the current at T1 and the current at T2 by finding the NMOS current at point 1 and finding the NMOS current at point 2. To find the NMOS current at point 1, what do I have? At point 1, I have for the NMOS VGS minus VT, and I have VDS. Of course, the input is already high, it's at VDD, so it is on, and this is VDD minus VT, and VDS is V out. Okay, since VDS is V out and V out is still high, it needs time to drop, then this is VDD. Okay, and then at point, okay, 1 second, sorry, maybe the connection is weak. And then at point 2, okay, the input is still high, but the output has dropped halfway. Okay, sorry, I lost, I think, the internet connection. Let me share again, 1 second. One moment. Yeah. Oh, okay, I need to assign myself again. Okay, so, okay, let me share again. Okay, so at point 2, the input is still high, and the output has fallen halfway, and therefore VGS minus VT is still VDD minus VT, okay, and the device is on, of course, and the VDS is now at V initial plus V final over 2, which in this case is VDD over 2 لأن هيدا CMOS inverter, okay. Now, from these, from IN1 and IN2, I can find IN average, and therefore I can find IC average, okay. Anybody has any questions? Okay, so let us then now move on to the next slide. Okay, just one minute. Okay. Okay, so let me now look now at the slide here, what has been written, and I will clear it up for you later. So, pardon me. So we have here the T1, pardon me, this is my little daughter. V out is still high, so V out is VDD at time point 1, and we find the current as function of VDS and VGS of the transistor. And then we look at the same information at time point 2, and at time point 2 we say that V out has switched to half of its initial value, and accordingly we can calculate the current from VDS equal VDD over 2 and VGS equal VDD. Okay, now if VDD is very large, the chances are the device will be in saturation, and the average current is IT2 plus IT1 over 2, and the delta V in absolute, these are absolute values as we said, is equal to VDD over 2. And accordingly, the delay will be C delta V times I average, which is C times VDD over 2 times I average. Okay? Great. So if we plug in all the information, the delta V is proportional to VDD. The current more or less it will be a saturation region current لأنه هو بالآخر towards the end the NMOS pulls the output fully and it goes to the linear region, and therefore the delay is proportional to CVDD over VDD minus VT squared. So if VDD increases, the delay is going to decrease لأنه هيدي 1 degree هيدي degree 2. Okay, as VT increases, the delay is going to increase. ليش؟ لأنه إذا VT كبرت هيدي ال quantity حتصغر and therefore the delay is going to shoot up. Okay, okay, so the VDD, if VT increased, pardon me, this whole quantity, if VT increases, let me erase this. So if VT increases, this whole thing is going to drop and the delay is going to increase. So that is another reason. هي ال VT إذا كبرت يعني the device will have less overdrive, right? And it will be weaker. And then as C increases, of course, the delay is going to increase. Okay, so as C increases, the delay will increase. فإذا the different factors that affect ان VDD, VT and the capacitor طبعا ال current لأنه ال width للdevice لأنه كل ما كبر ال width كل ما صغر ال delay, بس we will talk about the width of the device later. Okay, so let us now look here to see what is the the other possible way for computing the delay for the inverter. So the second possible approach is the RC delay. And by RC delay, I mean I don't want to calculate the average current. Maybe I want to find the equivalent on resistance. يعني إذا I have a high to low transition at the output, then we replace the NMOS with RN and we find the effective RC time constant. Okay, so we need to find the effective RC time constant. And then in a similar fashion, if the output is transitioning from low to high, I'm going to replace the PMOS with a resistor RP, and I'm going to find the pull-up RC time constant, but based on R effective, because R effective depends on the width of the transistor. Let us look at the RC delay and the effective R. Yeah, بدي اجي طلعه من التايم T1, T2 from complex equations. Let's forget about these. And this would be the accurate method. Okay. And for the accurate method, we're going to assume unified current model. So نرجع نلحق الexample which we just solved. At T1, I had VGS equal VDD. هيدي لما كان output is transitioning high to low. Okay, and VDS is equal to VDD. And I can now check طبعا VDS is كبيرة, VGS is كبيرة, so velocity saturation, it will be in velocity saturation. At time T2, VGS equal VDD, we found that VDS equal VDD over 2. So if VDD is large enough, there's a good chance that I will be in velocity saturation. And then I will have the resistance is really, since I look here, when the output at T1 is equal to VDD and I have some I of T1, then R of T1 will be equal V out of T1 over I of T1. And in a similar fashion, هيدي هي أول quantity. In a similar fashion, at time point T2, I calculate the output is at VDD over 2 and I calculate I of T2 and I write V out over I at that specific time point and I take their average and I will end up with the resistance for the TP high 2. Okay, so we know how to calculate, but sometimes we just want to rush through it. So we will follow the approximate table method. And in the approximate table method, For purposes of the short quiz, we said we will give you that if I have some Rn when the W equal 1 micrometer, then if I give you another R, W, let us say 10 micrometer, let us say it is 1 kilo ohm, what you will say is that the resistance will be equal to 1 kilo ohm over 10, because as W increases, R is going to drop. The current increases and therefore the resistance is going to drop. اوكي ما قلنا ال R هي already هي V out على R and I is really some function of W. So if W increases, R is going to drop. Great. هلا for purposes of here, the more generic data is that we will be given some R value, like say 1 kilo ohm when W by L is equal, or when L by W is equal to 1. هيدي ليش هن بيقولوها هيك؟ لأن هيدي هي L over W, and this is really okay, is referred to as 1 kilo ohm per square, meaning when L by W is equal to 1. Now, if you remember when we talked about the sheet resistance, we said if I have W and I have L for any material, transistor, channel, wire, okay, I count the number of squares, which is L by W, and I multiply by it. And as somebody gave me the R sheet, which is kilo ohm per square, I multiply the R sheet by L by W, and I find the effective resistance. Now, what does this mean here? It is simple for me here. What this means is that now, if I am given that the resistance for the transistor is 1 kilo ohm per square, then I'm going to say when my R effective, and I know that for my transistor W by L is 10, then I'm going to say it is 1 kilo ohm times L by W, which is 1